Hello and welcome everyone. I'm Ines Thiers of the AAA Code project, and today I'm joined by João Cabral and Rui Mao. João and Rui are from our partner institution, Imperial College London, and they work in the Department of Chemical Engineering. João leads the Polymer and Microfluidics group there, and Rui is one of his PhD students. Today they will tell us a bit more about their life and their contributions to the AAA Code project. Hi João, hi Rui. Thank you for joining me today. Let's start with our first question. Could you tell us a bit more about the main focus of your research at Imperial?
Hi, Ines. Good afternoon. I perhaps before we do that, I just wanted to introduce ourselves a little more. So my name, as you said, is João Cabral. That's a Portuguese name. That's Portuguese for John. I'm a physicist, and I have, I guess, over the years become interested in chemical engineering. So in translating solutions that are from physical chemistry into, I guess, applied to societal challenges. And so this research group that we have at Imperial Chemical Engineering really focuses on scaling solutions that are based on physical chemical principles that really can tackle the largest, the most pressing societal challenges. I guess in my career, I've taken a few steps really in different directions. So after a PhD in Chem-Eng, I joined an Institute of Standards and Technology, NIST, in the US, and then came back as a lecturer in chemical engineering. And broadly speaking, our group focuses on complex fluids or soft materials. So typically these are not unlike our own biological I guess, nature. So they are typically comprising polymers, surfactants, colloids, proteins, and these types of both simple and complex fluids can exhibit what we call, I guess, emergent behavior, when the sum of the parts is much greater than the individual constituents can deliver. And in the context of this AAA Code project, we're really looking for out-of-the-box solutions to, I guess, a grand challenge of AMR, so antimicrobial resistance, or effectively keeping ourselves clean, saving lives, really addressing some of the pressing issues that I think have become more recently apparent due to the COVID-19 pandemic, but have been there all along and really have increased in I guess, in need and urgency over the years. Hui joined our group as a postdoc, so she's an experienced postdoctoral researcher in the field of biopolymers and specifically in cellulose. So I'll let Hui introduce herself, please.
Okay, hello everyone. Yeah, my name is Hui Mao, and I'm a research associate and joined in João's group 2 years ago at Imperial College London. Yeah, and my research connects closely with João's, but I focus on bio-based materials more. And since joining the AAA Code, I've been using the nanofabrication methods to give these materials new functions. And for myself, it's about showing how sustainable materials like the nanocellulose can be turned into high-performance coatings that are good for both people and the environment.
Okay, thank you. Maybe Hui, can you explain us a bit more? How did you end up in London and at Imperial College specifically as a group of João? How did that, evolve actually?
Yeah, and I did. Since I my PhD and I did the research about the bio-based materials and from the pulp and into the nanoscales fibers and João's group and for the AAA Code and specifically for the nanopatterning and to form the different patterns on the surface. So that's my interest because we did a lot on the chemical modification before, and we know with these structures, tiny structures, it can give better properties as some unknown things will happen. So I'm very interested in this project, and then I joined João's group, and now I'm doing this.
Okay,
so
that's very
Ines,
cool.
it's more like that. I I found Hui because
Ah,
we needed effectively to assemble a team that
mm,
could work across these interfaces. So, as I said, I'm a physicist and with sort of training in chemical engineering. Hui, I think, is more of a materials chemist, so
Yeah.
somebody who bridges materials and chemistry, and together with another member of our team, Hisei Lama, who is really at an interface of, I guess, physics and engineering. We kind of closed the loop in trying to deliver solutions that are not based on, I guess, chemistry to the challenge of this antimicrobial resistance, or AMR. So if I may, I'll introduce just a little bit this topic because it's often mentioned that there is an issue. Perhaps we go to the doctor and we are told, well, you should avoid taking antibiotics, or that's to avoid antibiotic resistance, for example. So an antibiotic is a type of antimicrobial, and then the challenge overall is that microbes, that includes bacteria, viruses, fungi, parasite, all of these microbes can eventually develop or mutate into strains that resist these antimicrobials. They become what we call superbugs. So the existing antimicrobial agents have an increasing challenge because as we administer those more frequently, then we have uh, so I guess we can think of the overuse of these antimicrobials has really caused a huge increase of these superbugs that we can't deal with. Of course, this affects predominantly regions that are poor in the world, so low and mid-income regions, and it affects trivial things. For example, you might have a small infection, or you might go for a small surgery, and those can lead to an avoidable death because of this growing issue of antimicrobial resistance. So at the moment, the estimates are that this challenge it kills about 1 million people or so annually, but it's growing rapidly, and so the forecast is that within a couple of decades, that number will outpace, for example, cancer deaths and uh, a number of other conditions. So it might become the most significant health condition that affects us. I mean, by comparison, if you think of road deaths, for example, that's commensurate to what we have at present. So it's about 1 million as well per year, and so it's a big challenge, but
mhm.
importantly, it's a growing one.
Yeah.
So antimicrobials are chemicals, effectively chemical solutions to this challenge, and the type of approaches that we are pursuing, sort of out of the box here, are rather, I guess, physical or
Mhm.
physical chemical based, and so we take inspiration from nature, and we look around to uh, plants, insects, and so forth, and we kind of ask the question, well, how do they do it? They clearly are not administering these chemicals, and yet they seem to be able to, by and large, keep surfaces very clean. And I mentioned surfaces because that's the thrust of our project, is to develop
Mhm.
coatings that can be resistant to microbes, including bacteria, viruses, and so forth. And the hot spots, if you wish, the most dangerous uh, uh, sort of targets of our research would be what we call high traffic areas, like
Mhm.
hospitals, public transport venues, so tube stations in or metro stations, underground stations, depending on how we call them, train stations, buses, so forth, but as well as hospitals, schools, etc. So we, I guess, Hui ran a very interesting outreach session, so that she might tell us a little bit about, because we we look at sometimes the most vulnerable, so kids as well as elderly people, as as perhaps targets of our research. And who do you want to talk about maybe that outreach
Yeah.
activity you ran?
Yes, and so far we have run successful outreach already to introduce our AAA code project, and we face to the case from 6 years old to 15 years old, I think, and they are very curious. And the first of all, we open the question, where we got the microbes, and all the kids they are very interesting, especially the adults, their parents, they really want to tell the children to clean their hands before eating or something. So we open the question, yeah, very happily. And then we have them to see what happened, what the microbes spread on their hands. And we ask them where the microbes from the surfaces. So we come to what we are doing. So we got the microbes from the surface. If we can do something on the surface to stop the spreading of the microbes, and then we can stop we can protect the people. So the case, I think they got impression, and after our activity, they will definitely wipe carefully or clean before eating and in the playground. So yeah, we had very good experience on this. Yeah.
So I
That's
mean, just to
amazing.
one of the ones that I love about these demos is that you can rub your hands with some
Hmm.
kind of UV glowing, effectively lotion, and then do your very best at wiping it all off. And then you put your hands in some kind of under some kind of UV light, and of course any residual amount of this lotion on the surfaces of your hands, fingers, nails,
Hmm.
etc., will glow up. And it's amazing how, I mean, kids. Okay, we might expect kids to be rushed and not so focused on detail, but you should see the faces of the adults when they do that, and they realize how poor of a
Yeah.
job most
Yeah.
of us do when we try to wipe our hands. So I think the first thing is that microbes uh, are not necessarily negative, right? We have a
No.
great proportion of our mass in our body
Hmm.
are indeed microbes and parasites,
Yeah.
etc. So we,
Yeah, of
we
course.
we need them. We have a relationship of cooperation with those, but there are these class that cause infection,
Of
and those
course.
we need to deal with in a more, I guess, sensible way. Because right now our trajectory is worrying that the AMR
True.
deaths are increasing rapidly.
Yeah.
So I think there's lots of inspiration from nature that we can take to look at out of the box solutions, and our component of the project is really part of that.
Yeah,
Yeah.
I think what you're doing is amazing in several ways. You nicely explained the pressing issue of microbial resistance, which is indeed increasing and causing a lot of deaths annually. And I think it's very nice to see how you actually combine forces. You have a multidisciplinary approach actually to tackle this pressing issue and create solutions. And on top of that, you actually create more awareness by doing the all the different activities with the kids, as you just explained, which is also a very important part in the solution, actually creating more awareness. So I think you're doing indeed an amazing job at that. You nicely explained nanopatterning already. So taking actually inspiration in nature, looking at the patterns, try to implement it on surfaces or materials that we use as humans. Can you go a bit deeper into the nanopatterning, how you can actually achieve those patterns and what other kinds of applications it might have beyond the antimicrobial effects it has?
So, if I may, just to start briefly on where the idea comes from, right? Because we are certainly not the first people to think about this, but where we are, incidentally, at Imperial College London, in the middle of this kind of museum sort of cluster, we are next to the Science Museum and the Natural History Museum, and they have actually quite amazing collections of specimens that have been collected over the years across the globe, in fact. And there are a number of stars amongst these. And those count, for example, dragonflies, cicadas, certain beetles, and that exhibit particularly exceptional antimicrobial resistance. And so the natural thing, as humans have been doing for a millennia, is to try to copy nature. And so the first stages of this was only to find out, how do they do it? And it turns out that biologists and geneticists know quite a lot about the different strands of these species and their behaviors, their habitats, and their performance in terms of antimicrobial resistance, in a sense. And so we partnered with them to collect and characterize a bunch of specimens. And what we find, we and others, is that there are a number of features that come up that are, I think, pertinent to the topic of morphogenesis, the emergence of shape and form. And what you find in some surfaces is that they are spiky, a bit like a nail bed. And so you'd think, okay, well, there's something special about some types of spikes. The spikes seem to have properties like they have a high aspect ratio, so they are taller than they are wider. And they are, as Hui mentioned, at the nanoscale, so typically in the few hundreds of nanometers. And if you think that microbes have dimensions that are, roughly speaking, of the order of, say, for bacteria, a couple of microns, it seems that one mechanism can be effectively what we call biocidal, so it's an actual killing and impaling of the microbe through a deformation of that membrane that eventually is perforated and spills out effectively to the contents that are contained within that cell membrane. So that's just to mention one example. Other examples seem to have slightly, tortuous surfaces, so zigzaggy type surfaces that are commensurate with the dimensions of the microbes themselves, and that seem to confuse their ability to form films, or sometimes biofilms, we call them. So what we've done, based on these observations, is then to take a step back and think, okay, well, let's think for a second, what are the different stages of, say, a biofilm formation? Because we know that it doesn't happen all at once. So a microbe needs to first approach a surface, and then there's a stage that's called initial attachment. They will figure out, is this a good place to attach or not? And so that's every stage you can think of as a possible intervention point. And so the first stage, this initial attachment, where you think maybe a bacterium that is maybe suspended in a droplet that might have been, sneezed out of a child or an adult or whoever onto a surface, that you can think of this as a pocket of liquid, and bacteria will sense that interface to gauge whether this is a good interface to attach. Then if that happens, then they might attach irreversibly. That's the next point of intervention. They will eventually maturate, they'll form a colony, they'll eventually grow into a biofilm, and then that's the green slimy stuff that we see eventually. So at every stage, we seem to have natural counterparts that are based on these physical strategies that seem to be able to interfere with these processes. So from spiky surfaces that could kill, and but if we go even earlier, you can think of surfaces that bacteria just don't want to attach to. And so Hisei in our team has been looking at effectively the fundamentals of wetting and spreading. So that's what happens when a droplet comes close to a surface, and that could be a droplet of something that we transfer from our hands, say to a some kind of pillar within on a bus or on a public venue, or something we sneeze onto a surface. And so we ask the questions, what would it take to convince that surface to roll off that droplet, so that you don't even create the possibility for that initial attachment. So to create sometimes called super hydrophobicity, since those droplets are often water-based. And so it turns out that these types of surface patterns can mimic, for example, the common example that we talk about is the lotus leaf that exhibits some intricate topography that is quite undulated at a couple of length scales that seems to always get rid of water. And so to structure these thoughts a little bit, you can think of the proliferation of bacteria or microbes in general to have a couple of stages, let's say 5 stages, and there seems to be a physical counterpart acting point at all of these 5 stages based on simply topography that, and this is a big hypothesis for our project, that we think that microbes cannot outsmart. And so this is a kind of a leap of faith assumption. We have not tested that, but that's one of the bits that really excites us about this work. Hui, would you like to maybe continue on how the stuff is made, in fact?
Yes. Yes, first of all, so we want to target to the antibacterial properties to make the antibacterial surface. So based on João just mentioned, there are two possible mechanisms behind, and one is the anti-attachment, one is the biocidal. So based on the different mechanism, and we need the different aspect ratio, different patterns of the on the surface. And for the anti-attachment, it seems we need the different shapes. So we don't need it to be super sharp, super high aspect ratio. So we use the nano imprint lithography to make this kind of pattern. But as we know, the bio-based material, they are not they are versatile and they have their own nature, like they are hydrogel when they can absorb a lot of water. And so when we use it, how to evaporate all the water, how to dry it is a big challenge. So based on this, and we develop our one method, and we tested the different substrate, the different filters, till we find some route for the vapor to escape to faster the drying process. So we can short this period in 5 minutes. So in the lab, so far it's a quite efficient method to make the different patterns on the surface. And one thing for this method is the mold, and we all know for the nano imprint lithography, the mold is the biggest problem. And in our lab, and we have a method, it's called wrinkling method, and we can make different shapes of pattern in a large scale way with the plasma. So we use the PDMS and we use the plasma to form the glass layer on the surface. The mechanism just like we have wrinkles with age. So this is a very potential, very practical method. And based on this, and we have the mold, and then we develop a new method for the nanocellulose hydrogel, and then we successfully achieved the patents on the nanocellulose. That one we target to the anti-attachment mechanism. And also we inspired by nature, and for the cicadas, and they have the high aspect ratio pillars on their wings, and we also want to get a high aspect ratio pattern. And the way we are using so far is called ion mailing. So the ion mailing is a physical process. So we use the argon ion to replace or to remove the items on the nanocellulose, and then we achieved the high aspect ratio pattern. And we are still developing the process, but we achieved the super hydrophobic property already, but we are on the way to get a super high aspect ratio. Yes.
Okay, that's very interesting. Maybe to like wrap up, or to for people who are less aware in the field, can I compare the mold with like a stamp you put onto a paper, and the ion milling? Is it like really shooting ions to create a certain pattern then in the paper? Is that how you can visualize it a little bit?
Yes, for the white imprint lithography, it is just like the stamping, but the difference is for the nanocellulose, we can't stamp it on the dried film because it's elastic. So if we simply stamp on top, and you will see the pattern become less and less with time. Yeah, so for our what we modified is we form the pattern when the nanocellulose is still white. So that means it formed during the drying process. So it's very stable. And we tested the stability, and we found within 1 year, it's still as the beginning. So still the same as the beginning. So this is the difference what we did. And for the iron melting, yes, it is. So the iron will just come to the surface and just scatter away the atoms on the surface. But the mechanism is still on the way to discover it. Yeah, we need to find the mechanism behind, but obviously it is. So when the iron come to the surface, it replace or it just remove the surface.
It's a very cool approach. It's very interesting to learn about it. It's not that convenient, and I think you're doing an amazing job at it. Maybe one last question. João, you're also part of the BEST network, which brings together scientists, engineers, industrialists, investors, and so on, working on antimicrobial materials. You briefly already touched it in the beginning, but why do you find it important to be part of such multidisciplinary community?
You bet, Ines. So I feel increasingly, maybe as I get older as well, that as much as we love the fundamental research, that I think there's nothing more exciting than see the translation across this, what we call technology readiness level stages, the TRL stages. And that requires really an integration along the value chain. And I mean, it's so common to find technological solutions that seem compelling that never see the light of day because we've missed a trick somewhere. For example, the material was too expensive, or it cannot be scaled properly, or cannot be applied properly, or cannot be, I mean, it doesn't fare well in terms of some kind of performance metric, or simply, there's no market. There's no market appeal for this, so we we can only unlock the benefits of these types of technologies if we integrate along the value chain. And this needs cooperation because we all have our skill sets and our basis of, excellence. And those communities are amazing to not only bounce off ideas of each other, but also benchmarking against competitors. I think benchmarking performance is really important. So often cases, I might make claims about my solutions, and then other people might challenge those claims because the criteria that I've used to test them, for example, against a specific, I don't know, in this context, against a specific microbial strain, might be somehow inadvertently biased, and so might not reflect the reality on the ground. So I really do think that, especially when it comes to these grand challenges, I think we need to put some sort of traditional methodologies of work aside and work collaboratively because they are just too important to, and there are too many lives at risk. There's too much at stake for us to, fail. And it might not be, we love this approach. We mentioned this wrinkling or this autonomous patterning technique because we feel it's, from an engineering point of view, it's naturally scalable, but we're not married to it in a sense that she also mentioned another ion milling approach, and there will be many others. So although we might have our favorites, we want to see the problem solved. So as engineers, we'll roll up our sleeves, and if our solution is not as good as some other ones, we'll work on those ones instead. And so you can only do that kind of benchmarking exercise within a network that is interdisciplinary and has the investors and the consumers bases and the regulators and so forth involved because it's just too important.
Yeah, I agree. I agree. What you say is so true. And I think it's very good that such network exists. And I hope to hear more about it in the near future and see what kind of solutions this collaboration can actually bring together. I feel like I still have a lot of questions, but let's leave it maybe at this for today. Thank you so much for your time, both of you. It was a very interesting talk. I learned a lot. I hope the listeners also learned a lot. Also, thank you for listening and hope to see you next time.